Hello guys, as I promised you, I will record a YouTube or two about chapter 20 and I will focus on the main points in chapter 20 that we are concerned about, and I want to start with the summary of chapter 20. As we mentioned in the class that chapter 20 is about magnetism. Magnetism, we are talking about magnetic field. Maybe the most thing that we were familiar with, that magnetic field is related with magnets. Magnets, it has north, or the magnet has north and south poles. And all these things that I have already told you in the class, that you have to go through section 20.1 and almost 20.2 and go through the main pictures that are talking about the magnets and the magnet properties. All right, so I will not go through that now. Also, as we explained, that if we have a current and that current is passing through a wire, simple, there is a current and it's passing through a wire. All right, this is the wire and there is a current is going through that wire, then there will be a magnetic field around that wire. All right, so if we have a wire with a current passing through the wire, there will be a magnetic field going around the wire. Sometimes we don't feel it because the magnetic field is weak. Otherwise, through any wire where an electric current is going on, there will be magnetic field around that wire. Now, because of the presence of the magnetic field around this wire, so we have wire, if we have wire with electric current, the electric current, the passing of the electric current creates magnetic field, which is B. All right, because of the presence of the magnetic field around the wire or around the current, there will be a magnetic force on that current. It means the presence of current creates magnetic field, but at the same time, the presence of that magnetic field will create force on that current. You see, like something creates something, but that thing will affect on the current with a force. So passage of current will create a magnetic field. The presence of the magnetic field will create magnetic force. You see, this is not the electric force that you have maybe covered in chapter, I'm not sure, 16 or 17. This is basically the magnetic force. But since in this chapter we only have the magnetic force, we will just refer to it as F. So now we know the consequence of the things. The presence of the current create magnetic field. The presence of the magnetic field will affect on that current with magnetic force. That will be better even. The value or the magnitude of the magnetic force is equal to the current itself, which is basically the origin of everything, times the magnetic field that is created due to this current, times the length of that wire. All right, like if this is the length and the current is passing through this sector, all right, so this is the length of that wire times sine of the angle between I and B. All right, this is one very important relation in chapter 20. All right, good. So it's ILB sine theta. You could be given that in the formula sheet, but you have to understand what everything refers to, because in the formula sheet, as we know, it's only the formula which is given, but he will not be telling you what is the meaning of everything. And the other thing, even I am trying here to look up the formula sheet, and it says F is equal L or I LB sine theta, but you need to figure out theta is between which variables, and what is I, what is L, what is B. All right, so this is one very important formula. I will get back to this formula up there in this document, but first I am going, as I told you, in the summary and the focus of the things that we are covering in chapter 20. Now, so we were talking about current going through wire. What is current? Current is a flowing of charges, right? Flow of charges. What if we don't have current for a moment and we simply have a moving charge? The current was a flow of charges. Now we have simply a charge, and it's moving in a magnetic field. All right? Same thing. Due to the movement of the charge in a magnetic field, also there will be force on that charge. Again, here, during the passage of the current in the wire, with the presence of the magnetic field is acting on the current with a magnetic force. During the movement of the charge in the magnetic field, there will be a force acting on the moving charge. Good. Now, let's see the formula, which is also one other very important formula in this chapter. It's, if you see, let me write the other one down here. I times L B sine theta. And here, instead, we don't have full current. We have simply a charge, and it's moving with velocity v in a magnetic field. And this is sine theta, which has a different meaning now. This theta is between, we mentioned I and B, right? And this theta is between, we don't have now I, the movement of the charge is represented by the velocity. Now, so this is the angle between velocity of the charge and the magnetic field. All right, so this is between I and B, and this is between V and B. All right, because this is the velocity of the charge. And see here, it says moving charge. So if it's not moving, there will be no force. It's the movement of the charge in the magnetic field which will create the force on that charge. But if you see, guys, these give us only the magnitude of the magnetic force on the current and on the charge, but it doesn't really give you the direction of that force. I will skip this formula. I will skip those. Okay, now let's go back to the beginning of the chapter. So these are the two very important formulas. Now, I know I am going from the end of this file or document till the beginning. I am not starting the traditional way from the first page till the last, because I know we talk about it in the class. Now, I just mentioned that F is equal ILB sine theta and F is equal QVB sine theta. These both are only to calculate the magnitude of the magnetic force. All right, one on the wire, on the current, and the other one on the moving charge. Here is how to determine the direction of the magnetic field here. This is to determine the direction of the magnetic field, and these two to determine the direction of the magnetic force. This one is related with F is equal I LB sine theta, and this one is related with the formula F is equal Q V B sine theta. All right? Okay. So guys, if you see here, if you recall, we mentioned this little bit in the class, but still I'm going through it again. This is the easiest one, which is right hand rule. By the way, the hand rules, they are all the right hand. You cannot use both right hand rule and left. There is nothing called left hand rule. It is the right hand rule. Right hand rule number 1 is easy. The thumb is pointing towards the direction of the current. This is the easiest one. And if you wrap the fingers around the wire, all right, this is the direction. When you curl your fingers around the wire, pointing your thumb in the direction of the current, the fingers will point towards the direction of the magnetic field. Again, you point your finger towards the direction of current, and then you curl your fingers, and that will be the direction of the magnetic field. This is easy because this is just simply the magnetic field that is produced by passing current in the wire. So you simply, raise up your thumb, or by the way, it's not always raising up. What if the current is downward? Can you do that with me? You go down with your thumb, and then you curl your fingers, and that will be the direction of the magnetic field. What is the difference between the two cases? When the current is up, the direction of the magnetic field is counterclockwise, right? You can see. And if your thumb is down, then the direction of the magnetic field clockwise. Let me do it again. This is the direction of the current. What if somebody tell you, what is the direction here of the magnetic field? Out of the page or in the page? It's out of the page, right? At this moment, it's out of the page, and then it curls. So it goes into a circle. But if the current is down, you can see that your thumb will go down. And if somebody will ask you the same thing, what is the direction of the magnetic field here? It will be into the page. What about the direction of the magnetic field at this point? It's curling the fingers up, out, and in. So in this point, at this point, it will be in. What about here? You'll go with your thumb down. So the magnetic field direction, here again, it is the magnetic field direction. If your thumb is down and you are curling your fingers, here it will be into the page, and here out of the page. All right? This is as easy as we can explain it. And look at here, we are only dealing with two things, I and B. I and B. So it is a simple one, I and B. Just go with your thumb to the current and curl your fingers, and this is right hand rule number 1. Now right hand rule number 2, when we have current and magnetic field, and now we want to know the direction of the force. See, now here he will give you, they will have to specify. Okay, the YouTube will be over, so let me end the record here, and I will come back in the other record for right hand rule number 2.